Okay, class, so this is the continuation of the Day 58 Aufbau assignment. Again, an explanation of what this is and how it works is in the video notes. And somewhat at the beginning of this assignment, I go into some detail on it as well. So you should view that before you view this video. What we're going to do is go ahead and for about 4 different elements, we're going to find out, we're going to draw and also write out what the electron configuration is. So for boron, we see that boron is right here. It's at the beginning of the second row p orbital. So the 2s orbital is right here, and the 2p orbital are these 6 elements right here. It's the first element in the 2p. So what we do here is the 1s. Boron has a full first orbital. So we draw an up arrow and a down arrow, and that fills So we draw an up arrow and a down arrow, and that fills the first orbital. Now we're on to the second orbital, and that's represented by the first 2 rows of the periodic table. Again, the first 2 rows represent the s orbitals in any row. So that's going to be an up arrow and a down arrow. And so we're here. Now we're going to jump over here, and this is where what we're shooting for is boron. And it's the first electron in the 2p orbital, so it goes right there, and that takes care of that. Now the electron configuration, the way you write that is, you simply say we've got 2 electrons in the 1s orbital. The way you denote that is 1s and then a superscript 2. It's not a square, it's not a math equation, it just means the 1s orbital and you have 2 electrons in it. Now we go to the 2s orbital, and we have 2 electrons in that as well, so we put a 2 there. And finally we go to the 2p orbital, and it has just this 1 electron. You do not break it up by px, py, and pz when you write this notation. It's just the p orbital as a whole. Alright, now the condensed electron configuration is designed to make this shorter. So what you do is you start with the noble gas that's in the row before. So if we're at boron, that's in the second row. So the noble gas at the row before is helium. So what you do is you take that noble gas, you put it in square brackets at the beginning. So now we've basically covered everything up through helium. And now we continue from helium down here doing what we did before. So this is 2s, 2. And finally, over to the p orbital, 2p1. Now you see that really didn't make it any shorter than the regular electron configuration, but as we get further down the periodic table, you'll see that it makes a big difference. Alright, let's move on to aluminum now. Alright, and for aluminum, aluminum is right below boron. It's the first element in the 3rd row. So what we're going to do is draw our 1s orbital. Aluminum is already drawn there. Aluminum has a full 1s orbital. Then 2s. Everything in the 2nd row is going to be filled since aluminum's in the 3rd row. Everything below that has to be filled. So there's an electron up and an electron down. Now we have to fill the 2p orbital, and it's going to be completely filled because we got to get all the way down to the 3rd row. But I'd like you to practice doing it in the proper order. So you do an up arrow, and then you don't put the down arrow in right away. You put in an up arrow in the next subshell and an up arrow in the next subshell. And that's called Hund's rule. And Hund's rule says you have similar electrons of similar spins, in this case up arrows in other words, and you spread them out through all the subshells until you put 1 electron in each subshell. Now we need to come back and we need to put a down arrow. And the down arrow represents an opposite spin from the up arrow. Electrons are negatively charged, so they repel each other. But what opposite spins does is it magnetically kind of attracts them to each other, so they're not totally attracted to each other, but they don't repel each other quite as much as they would if they had the same spin. You don't need to understand anything more about it than that. That concept of spin is simply opposite spin electrons have to be paired up in the same subshell. So that's called the Pauli exclusion principle. So let's review that. Aufbau principle says you stack things up from lowest energy to highest. Hund's rule says you take similar electrons with the same spin and you spread them out among the subshells before you start pairing them up. And then the Pauli exclusion principle says when you do start pairing them up, they have to have an opposite spin if they're in the same subshell. So we're going to put another one here and another one here. And now we have filled up the 2p orbital. An important point to understand is whenever you have a full p orbital, that's a noble gas. The only exception is the 1s orbital is helium. So we're going to put that in a block here. At the end of the 2p orbital, you have neon. So anytime you get to the end of a p orbital, it's not true of a d orbital or an f orbital. It's only true of p orbital. That represents a noble gas. All right, now we're off to the 3s orbital because we have to get down here to 3p to aluminum. So 3s is sodium and magnesium. So we're going to have at a slightly higher energy level than the 2p's is a 3s there. And now aluminum is the first element in the P subshell over here. There's 6 elements there, and aluminum's the first, so it gets 1 electron there, and we're all done with that. So that's the electron configuration for aluminum. Now we write it out in its notation. So it's just as simple as reading these. So you have a 1s, and you have 2 electrons in that. Then you jump up to the 2s, and you have 2 electrons in that. Then you come up to the 2p, and you have 6 electrons there. As I said before, you don't break this into px, py, pz. It's just the p suborbital. Okay, so it's 2p6. There's 6 electrons. Now we're up to 3s, 2 electrons there, and then finally 3p, and there's 1 electron there. You can see that's starting to get a little bit long there when you write it out this way. In the condensed configuration, there's aluminum. So we go to the noble gas in the row that's before, that's neon. And so we just put Ne in a block. And then we continue on where we started. So where is neon? It's at the end of this P, this full P subshell right here. So that's neon right there. So now we just write all of that as neon, and then we can just continue on with the rest of it. So it's 3s2 and 3p1. Okay? All right. All right, now we're going to go on to, I'm going to do strontium before I do copper. Strontium has a little bit of a trick to it. Okay, we'll go ahead and do, just had to stop the video there. Strontium before copper. Copper has a little bit of a trick to it, so I want to do strontium first. Now, if you look at strontium, it's way down in the fifth row, right there. Okay, so let's go ahead and fill this in. That means everything below the 5th row is going to be filled. So we just start off and we put 1s there, 1s there. Then we go to 2s, up arrow, down arrow. And then I would recommend you get in the habit of filling these in proper order just to make it a habit. You have an up arrow, you spread out your up arrows, Hund's rule, and then you pair up your arrows in opposite spins. That's Pauli exclusion, that an up arrow and a down arrow have to be paired together. So that takes care of that. So this we said was helium. This is going to be neon. You don't have to write these, but just so you have a reference, kind of where you are. Okay, then we go to 3s. Okay, we need to get all the way down to the 5th row, so 3s there. And then 3p. And then down arrows. Okay, so we're done with 3p. We're all the way to argon right there. So we're going to just call that argon. Again, the end of a P orbital, a full p orbital, is a noble gas. Not true of D or F. All right, 4s. So we're down here where potassium and calcium are. So that's up arrow, and now all of a sudden you have these transition metals jumping in here. And the fourth row cannot, the order must be S, P, D, and F. So here's the 4s orbital. It means that next the fourth row must have its p orbital. But this d orbital, which is the transition metals, jumped in there. So it cannot belong to the fourth row. The fourth row hasn't had its p orbital yet. So who does this d orbital belong to? It belongs to the row above, which is 3d. So just remember, a d orbital is always one row below its namesake row. So the 3d is actually in the fourth row. You just have to go down one. The 4d is in the fifth row, and so on. So we're going to fill up the 3d orbital, so it's up on all 5 of those subshells, and then go back and do down. Okay, that is not a noble gas. It's the end of a d orbital, but that's not a noble gas. Now that we finished with the 3d orbital, that was scandium all the way through zinc right there, now we're ready for the 4p orbital. So it goes 4s, 3d, 4p. You just follow the periodic table in order as it goes, as you go from left to right and then down, just like you're reading a book. Left to right, go down a line. Left to right, go down a line. All right, so 4p, we're going to fill all of those up. So up, 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 and then down. So now we have filled up a p subshell. That would be the 4p. That's going to be krypton. And now we're down to where we want to be, which is 5s, which is where strontium is, right there. So it's going to be an up arrow, a down arrow, and that takes care of the diagram for strontium. So let's go ahead and write the electron configuration for that. You got to start at the bottom and work your way all the way up. So it's 1s, 2, you have 2 electrons there. Then it's 2s, 2, and then you have all 6 of these p electrons are there, so it's 2p, 6. Again, don't break it into x, y, and z. And then it's 3s, 2, and then it's 3p, 6. And then you jump up to 4s, 2. And then you go to 3d. The 3d is at those transition metals in that from scandium to zinc. And so that's going to be 3d10. The light is shining on this. Okay, so if you couldn't see that, we went from 4s, and then you have a d orbital, but that can't belong to the fourth row because it hasn't had, the fourth row hasn't had its p orbital over here yet, so that d orbital has to belong to 3. Alright, so 3d10, and then we have, next up is 4p. Now p, the 4 is ready to have its p orbital right there, so there it is right there, so that's going to be 4p6. And then finally we move down to the 5th row, and there's strontium, so it's in the 5s, and it's 2 electrons. So 5s2. So that's the electron configuration notation for strontium. Now find your highest level p, full p orbital. So there's one, and there's one. This is the one that's the highest. It's the 4p6. That means that represents a noble gas. So if you want, you can put brackets around. You don't have to do that. Which noble gas? The one that comes before the 5th row. So it would be krypton. So all of this inside that block can be represented by Kr, by krypton. And then you simply write down anything that follows that, 5s2. And that's the condensed electron configuration right there. Okay, so that's how you do some of the elements that are farther down on the periodic table. Now, the last one we're going to do is copper. The reason I skipped this is it has kind of a quirky exception to it, but it's the one exception to this Aufbau principle that you should know. So let's go ahead and do that. So here's copper right here. And in the d orbital, it is the 1, 2, 3, 4, 5, 6, 7, 8, 9th element over. And you're going to find out the significance of that. If you read the notes, you'll know the significance of that, but I'll tell that to you in just a moment as we do it. So anyway, we got to build up everything all the way through 4s and then finally 3d. So let's go ahead and do that. So the 1s for copper is just going to have up one arrow and down one arrow, and everything gets filled in. I'm doing it in the order you should place them in. So now you have a full 2p orbital. And this represents neon again. Okay, then you have 3s, still building up, Aufbau. And then 3p is the same as 2p. And then down arrows. Spread them out, Hund's rule. Up and down arrows together, Pauli exclusion principle. Alright, next is 4s down here now. So that's going to be up and down. You got to fill in that one first before you go to the d. And now here we are where copper is going to be found. It's in the 3d orbital. So we're going to do up arrow, up arrow, up arrow, up arrow, up arrow, and then down, 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 and down. Now that would seem that that's the correct configuration for copper, but there's a rule that says that atoms are more stable when they have either half-filled orbitals or completely filled orbitals. So if we count how many elements are in the d orbital, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So manganese would be halfway through that d orbital, and zinc would be all the way through that. So if you look at copper, it's 1 electron away from zinc, from being a full d orbital. So it wants to add an orbital, add an electron, so it has a full d orbital. That makes it more stable. That's all you need to understand about that concept. You don't need to understand why it makes it more stable. It's just one of the laws of nature and of chemistry that happens. So what we want to do then is we want to put an additional down arrow here so that it now has a full d orbital. But where did it get that down arrow from? It got it from the 4s. So I'm actually going to scratch out this electron there. That should not be there. The only one that should be there is that one. So it basically borrowed it from the 4s to fill its d orbital. So what happens when you go to zinc, the next element, what would it be? Well, it would pay back that s orbital. It would go ahead and put that extra electron there and refill the s orbital. But for copper, it borrows an electron from the 4s orbital so that the 4s orbital only has 1 electron. That would have been the same if we had been at chromium. It's the 4th element over. It would like to have a half-filled d orbital. That means it would add an electron, so it would be like the electron configuration of manganese. It would also get that electron from here, from the 4s orbital. Same thing. All right? So this is what it should actually look like. No electron there, but you put that electron there in the d orbital. So let's go ahead and write the electron configuration. So it's going to be 1, s, 2. Then you get to the second s orbital, 2, s, 2. Then you get to the p orbitals, 2, p, and you have 6 of those. Okay, and that's a full p orbital. That's neon. And then you get to 3s, 3, s, 2, and then you go to 3p. It's the same as 2p, 3p, 6, and then you go to 4s, and it only has 1 electron because copper borrowed that electron from the s orbital to put it in its d orbital. So it's 4s1, and then it's 3d10. So that's the complete electron configuration again. This is the exception to the Aufbau principle. There's not a lot of exceptions. There's some when you get down into the f orbital, way down at the bottom of the periodic table, but this is one that you'll see anytime you're in the d orbital. Okay, let's wrap this up by writing the condensed electron configuration. So the highest p orbital I see is this one right here, filled p orbital. It's got to be filled. Is 3p6. So I'm going to just put a block around that. And that 3p6 represents, in the third row, it represents argon. That's the noble gas. I actually didn't write it here. I could have written it right there as well. Okay, so that's going to be Ar. And then you simply write whatever else you have after that bracket right there. So it's 4s1, 3d10. And that takes care of that. So we'll work on some more of these in class. And anyway, enjoy the rest of your weekend. We'll see you on Monday.